All right, so my name is James Edmondson. I'm a Ph.D. from Vanderbilt University. Worked at Carnegie Mellon University for a long time in robotics mostly, vision. And what we're going to be talking about today is how do you get accurate, no false positive kind of objects and human activity detection out of your security cameras. Is there anyone here that implements AI in security cameras, or are they mostly vendors? It's like, how many of you implement AI in security cameras, like just out of curiosity? You can be shy, it's fine. Mostly I just want to know, what kind of audience am I talking to? What kind of depth can I go into? What would you appreciate? That kind of thing. So we'll go ahead and get started. What we're going to cover here is, what is the goal of human activity detection, object detection, those kind of things within security? What is the history of it? How do we get to this point? Why do we diverge in the ways that we did? What is the kind of huge driver in the VC market that's causing almost every other research to be gone from as far as a funding perspective in academia? And what is that doing for the future of security camera object detection and human activity detection? Okay, so we're going to cover a lot of topics. We've got about 45 minutes, at really a 50-minute session, but there is no session after this, and no one's going to come over and drag me out, I don't think. So if we need to stay a little bit for Q&A or something, let me know, and we can answer questions. There is a mic in the middle here. It's set up, so if you want to step up, if you're having trouble conveying your speech or whatever, just step to the center. I do not mind interruptions, like I said, so if you want to ask a question in the middle of it, that's fine. We don't have to wait to the end. And I know for me, if I have a question on slide 2 and it's slide 30 or 40, you might forget the question. So feel free to ask questions, not a problem. As I said, my PhD was in middleware for distributed artificial intelligence with robotics, so I was looking at swarms for mostly DoD research. Looking at how to do collaborative intelligence when you have no communications, which involves a lot of vision, which involves a lot of stigmergy, modifying your environment to tell other agents, hey, I've been here, this is what I'm doing. So I have a long history with both AI and formal methods, provable correctness in software. So how do you prove something correct 100% of the time when you deploy it? You're in the middle of a demo, you don't have the demo go terribly in front of NATO admirals and generals, that kind of thing. And for the last 6 years or so, I've been the CSO at Koshee in terms of robotics, AI, software, product innovation, and that includes some material sciences work. If you go to the top of the Venetian, look at the pool deck, our company, Koshee, designs the safety surfacing that's slip resistant, impact resistant, thermal resistant, so you can walk on it in the 120-degree Vegas, beautiful weather. All right, so just to kind of give you kind of a summarization of what we're talking about here, what exactly your goals are when you're doing object detection or human activity detection. You're trying to detect, especially for security cameras, generally you're doing people or things and activities in the images and video within a timely manner. So you need it to be quick. You can't be waiting 2 minutes, an hour, whatever it is for most security camera stuff, unless you're lucky enough to work on, for instance, forensics for law enforcement. Then you can kind of wait for a bit. You want to get the perfect answers. You're solving a crime. Obviously, if you have time, you can do that. But one of the goals you have here is be as accurate as possible with as few false positives and false negatives as possible. Now, if you're not familiar with what false positive and false negative mean, a false positive is whenever they say, this is definitely a person, but it's not. A false negative would be, there is a person, but you're not saying anything about it, all right? So that's the difference here. And we want to scale this to thousands of cameras. That's at least our goal at the company that I work at. We want to scale horizontally, and I think everyone involved in security cameras would also appreciate that kind of thing. Yeah?
Dumb question. I would think a false negative would be when a person is identified and there's no person. Can you just...
a false positive is whenever they say it's a person, but it's not a person. Okay, a false negative would be, they say there's no person here, but there is a person there. Oh, got it. That's the difference. Okay? All right. Last year I was at this conference and someone had the audacity to approach me and say, you couldn't have been working in AI for 20 years, it's only been around for 7 years. And this slide came about because of that. We've been doing machine learning especially since the 50s. And that 1957 first Perceptron, Mark I Perceptron by Frank Rosenblatt was a transformer. The thing that you see in ChatGPT and Claude and all that stuff, that was a mathematician building a neural network in 1957 with real hardware that processed images and said whether this was an X or an E, whether it was a circle or a square. It did simple shapes, simple letters, simple numbers, and that was 1957. So, tell your friends, if they approach me in booth 33106 and they tell me AI has been done for 7 years, the next time I'm not going to be nice. Okay? So, we were so thoroughly done with machine learning and computer science that we actually had a black period in the 80s where nothing was published, really. And we had no funding. There were 2 AI winters in machine learning that happened in the 80s and the 90s. And this was, it happened because, I'll be honest with you, it happened because people in the security industry and some other places promised some things in AI back in the 80s and 90s that never came to fruition. And you got a lot of VC funding, and it caused a funding dearth. Now, some of this also was in the DoD space. So the grant funding that essentially was going to a lot of these projects overpromised for what AI was doing, where it was at, essentially. And so we had a complete lack of funding in machine learning for 2 different decades, really, for most of them. And a lot of what you see, so how many know who Yann LeCun is? Facebook, chief scientist for artificial intelligence. And he actually just raised, I think, $4 billion or something for a company in France to do more machine learning or something. So in 1989, he created LeNet, basically with a lot of his own funding, and did a real neural network for vision classification of images as you would do today. So that's why he's famous. Most people don't realize it. They think it's because he's with Facebook. No, Facebook hired him because he was one of the key figures in creating machine learning as we know it today. But the 1970s saw your first backpropagation. It's the main way to train as you're doing machine learning and neural networks. All right. And really went to the schism in the 1980s. I'm not going to say I'm a part of it, but I am a formal methods guy. So I do like to prove correctness. And machine learning is all about doing the opposite of that. It's throwing training and other things at a problem and just saying, look, it works. And formal methods is like, no, seriously, I have to prove that it works. So there are 2 different schisms that happened here where you had 2 camps. It was like a religious feud almost, where one side was saying, you can't do anything, you suck, and the other side was saying the same thing about the other side. So it essentially split the funding, it split the focus. There wasn't a lot of machine learning and formal methods working together. In the 90s, you had boosting algorithms, which is what we call strong from weak learners. If you don't know what that is, it's basically making a really weak classifier. It's like, this thing does this thing okay, it does it all right, it's not a great thing, but when you combine a whole bunch of them, they create a strong learner, they create a strong classifier. So that was a concept that came around in the 1990s. Then you had a big paper in 1997 that really started the deep learning movement. There was one part of this long short-term memory that's kind of gone out of style. It was essentially more of a formal methods kind of thing where you could prove correctness on certain types of machine learning. And that was by Schmidhuber. I love those kind of names. It's Eugen, so it's spelled Jürgen, but it's Eugen and Schmidhuber. Long short-term memory was really replaced in all the focus by transformers, which is really probably, if you have anything on your security cameras that's doing something, you're probably using it, like Clip, Llama, any of those kind of things that have been like modern transformers. You're probably using that, but there is some interesting things to say about LSTM, long short-term memory, which, when you're looking to prove correctness or you're trying to say, why did it figure out what it said, you could probably do some things with that. It sequentializes learning. It takes longer to do, but you can learn something from it. So it might be worth looking at if you're interested. The big changes that caused the VC landscape to change and everything else, the funding, the direction, those kind of came about from the Face Detection Grand Challenge and the Large-Scale Visual Recognition Challenge. At that point, before 2010, machine learning was still relegated to the closet, even though you had Rosenblatt creating the first thing back in 1957. So they've been fighting against this tide for 50 years, 60 years. And these grand challenges where they started providing these huge data sets started really giving the chance to have enough data to learn on something and do a real useful classifier. Everybody following along so far? So like I said, that's Rosenblatt's machine, 1957. There's some really interesting papers on that. I know most people hate to read papers. I'm an academic. I apologize. But they're interesting. The math and everything that's behind neural networks, including recurrent neural networks and convolutional, there's a lot of it that's here. And if you've ever taken a course in machine learning, a lot of what, and Rosenblatt, the only reason he could build this because we were already talking about the math behind this before this. It wasn't like he just came out and he was the guy that came up with everything. But if you look at some of his papers or people talking about him, he was the guy in terms of that. He was the guy that drove the whole project. Everyone else is like, I'm just a worker bee, but I'm happy to be a part of this project. So there's a lot of great stories in computer science about this. You would think nerds don't value each other or whatever, but actually we maintain a pretty good history of everyone involved in a lot of these big projects. So From the 2000s, I'm just going to break this into a whole bunch of different categories. I'm going to lump some things together that if you are an academic, is there anyone here who is an academic, by the way? I think you're all industry. Maybe BYU over there. Yeah. All right, so I'm going to get in a little bit of trouble maybe from the academics, but I'm going to lump in some categories that no academic would, under any respectful academic would let me do. ResNet, LSTM, and transformers I'm going to put together because basically anything all those we're good at doing, everyone's using transformers for. So I'm just going to put that into a category so we can talk about it as a big lump, and any academic will be angry at me in the post-talk.
But could you define transformer?
So transformers, if you ever go to Hugging Face or any of those kind of things, it's something that there was a paper, I'm going to talk about that. I'm going to go into detail about it. So I'll give you a little preview. There's a paper by Google that is famous for saying attention is all you need. And what it basically means is, why look at one thing when you can look at all the things? And so multimodal encoders like feature extraction, image feature extraction, text extraction, audio extraction, all these things combined together and then paying attention to every part of it at all times is how transformers work. And it's impressive in that, I'll get into that. I don't want to go too far into that. It's a soapbox rant.
Just keep using the words.
Transformer, for people who are basically doing any kind of image detection right now, you're almost certainly using transformers. By the end of this talk, maybe you're not, but you're probably using it right now whether you realize it or not. So if you go to Hugging Face, if you go to these other places that give you like this cloud-based notebooks and stuff to train something on your own, most of the time they're recommending you try out these transformer models. They're the future, so they say. All right, so AlexNet was the big thing. 2012 was a big year of machine learning. You had AlexNet, you had the Google CAD experiment. The Google CAD experiment was essentially a self-supervised learning. So it's this thing where essentially they kind of built some features and they tried to make something learn those features without any person being involved in labeling the images. And so they were looking at YouTube videos, things of nature. They wanted to automatically label these things even though they'd never trained anything. So these started, for better or worse, a real push for self-supervised learning so that no people are involved. We're going to talk about that. Not really that good of an idea. It has not been very good or successful. There's a lot of reasons your models aren't working, and I would say Google CAD experiment had a lot to do with that. This is where you get grounding dyno. This is where you get a lot of these things that auto-label for you. So for better or worse, that's there. OpenPose is something we're not going to talk too much about that. I was at CMU, as Carnegie Mellon University, where they were creating this, so I was involved in a lot of this stuff when they were developing the features of this. This is the thing that does the actual perception of like having a stick figure guy that moves with your skeleton. If you're dancing, if you're doing whatever, it kind of tracks those kind of things. That's what OpenPose is. We're not going to talk about that very much because I don't think most of you are using it. So that's the only reason I'm not talking about it, okay? It was an academic project. It's being put into a lot of different things, but it's not very accurate, especially with hands. There is a hand model for OpenPose, but I don't know, man. So anyway, RCNN, YOLO, we'll talk a lot about YOLO, and we'll talk a lot about transformers. A lot of these things are going to go to the wayside, but if you're interested in learning more about these things, RCNN will also go over a little bit in detail, but only a few slides. Okay, so AlexNet's main contribution is that it showed that machine learning was at a point where you could use GPUs and in real time get results, and you could get accuracy. So in that big vision challenge, AlexNet beat the other competition by like 10 percentage points, essentially. So it brought the error rate down below 10%, and it was the first time that had ever been done. And the only reason that AlexNet was really possible to do that is because another researcher out of, I want to say Illinois, Urbana-Champaign, had actually created a data set of millions of images. And so for the first time, really, people had the ability to take this big model and train it on millions of images that were labeled reasonably well. And so that's another thing we'll get into in accuracy and understanding what this is. Accuracy, what does that mean, is a question you need to ask yourself for your security cameras. Because there's a huge difference between your training saying something has a mean average precision of 90% and actually being 90% in the real world. Huge difference. One of the things I try to tell students especially is, look, you can test for success, but you really need to test for failure. So that's like an engineering principle, okay? So like if your whole thing about testing for success is looking at your training data and only putting in the training data that gives you good training results, you're an idiot. I'm sorry, I'm not gonna sugarcoat it. I work with too many students. There's no reason to coddle this kind of belief. You need to test for failure. You need to test for the hard cases, and you need to make sure that your model isn't giving you something stupid, and that's how you reduce your false positives and false negatives, okay? If you put something in your data set that is bad, it will cause your model to learn something stupid. That's just That's literally science in this case, but it's true. But AlexNet was actually the LayNet 5. It was the 1989 model by Yann LeCun, the guy from Facebook, but it was larger and mapped to GPUs. NVIDIA GPUs came out. This is when CUDA really started becoming popular. So if you've heard of CUDA, that's that framework that everybody's using as far as it goes. It's hard for AMD to get in the market. It's hard for Intel to get in the market because CUDA is so good at helping you be fast, essentially is what CUDA is. It's a mapping inside of the GPU to give you a lot of parallelization. I don't know if you guys are familiar with CUDA. Can't go into too much detail. We only have so much time. So I'm lumping a lot of things in this bucket. Academics, I apologize. But you've got ResNet, LSTM, long short-term memory, and transformers. I'm going to bucketize these because everything that any of these were doing well has been put into transformers now. It is the technology. No one's getting funded for LSTM, even though there are researchers who are kind of self-funding and doing stuff today. Hard to get DoD funding, certainly, for LSTM, whether you go into any of the FR branches, the fundamental research branches of academia. So this kind of bucket kind of has a lot of residual connections. It's really trying to stop focusing so much on the short-term, the local search of training, and looking at the global aspect of it. It's trying to branch out and learn like what they call larger structures in a neural network. It's trying to get like in the future, like what should I keep in mind, or like time series stuff, things of that nature. That's what LSTM was really good at. It was essentially time series like looking at video, like not just images, but video, like over a video time. What is the sequence of things that does this? LSTM was developed for audio mostly, but it's okay in certain time series kind of evaluations. How many of you are doing time series? I assume everyone's just doing instantaneous image detection. Is that a fair statement? Okay. Time series is like if you have 5 frames, so you're doing 30 frames per second or whatever. So you're looking at 60 frames of information and not one. And then you're doing a model that can actually look at all of that. So that's possible. That's basically something you could do in transformers. You can do it in CNNs, convolutional neural nets, and you could do it in LSTM. And LSTM is actually just a recurrent neural network, but it's kind of a cooler version of it. And you can find ways to train those on like PyTorch. You can find them in Keras. You can find them a lot of open source places. They're not like completely deep into a paper somewhere they have to read. You can actually find them a lot of the same places you're training transformer stuff, like CLIP, like Llama, any of those kind of things. But basically what you can kind of take from transformers is they have encoders and decoders that essentially look at different channels of information. They could look at vision, they look at audio, they look at text, the boxes, the classes. They look at all these different things. They bring that into some kind of classifier that says, I'm looking at everything and I got this thing. I'm going to tell you what this is. This is the thing you're looking for, right? So transformers, the beauty of transformers is it can be multimodal, and that's just audio, video, whatever the thing is you're putting into it. If you ever hear anybody talk about tokens, it's literally a transformer concept. It has no bearing anywhere else. So if someone comes to me and I'm working on a YOLO model, you're asking me about tokens, I'm like, what are you talking about, man? I don't care anything about that. What do you bother me for? So a lot of these terms have become ubiquitous because transformers became the thing that took up 95% of VC funding and all of academic funding, right, in terms of machine learning. It's also the basis for most generative AI techniques. I could talk in length about this because I was part of a DARPA project called Symbiotic Cyber Design, Cyber Physical Systems, which was about generating robotic systems or warfighters or anything else up for the DoD, which was one of the first funded generative AI projects. But most of the time what you hear nowadays is really generative AI is a lot of times used to generate images of, I don't know, sexy anime waifus, whatever that thing's for. So RCNNs, they're no longer really funded. They're not really very much researched anymore. But they were pretty cool for a while. They gave us segmentation. Speed was better than what they were doing before in like AlexNet and other things. And if it weren't for YOLO, you would probably hear about RCNN. How many of you have heard of RCNN? Don't worry about it. It's fine. YOLO is about the only other thing you probably have heard of. Has anyone heard of YOLO? You only look once? Okay, so I think for most people in the security industry, if you're going to know of something, it's either transformers or YOLO. And we'll talk a bit more about those two because, first of all, there's no reason necessarily to look at other things that are maybe LSTM, but YOLO is definitely something you should know about. So this one was one of the first, it was the first thing to kind of bring together the boxes, the classification of something and the boxes and make it in a single pass so that it's fast. So it was fast, it was effective, it was very accurate, especially if you use bigger models and a lot of parameters. And we'll talk about the problems with YOLO and going forward, what the problems are in a minute when we get to the problems in the current space. All right, so right now I'm just trying to give you an understanding of what we're talking about before I go into detail about other things. Does that make sense? Is everybody following so far? Anybody like lost? Wants to throw something at the speaker? We're good? All right, great. So let's just remind ourselves of the goals here. We want to get detections in a timely manner. We want low latency, right? We're looking at 30 FPS. We're looking at whatever these from cameras. We got to process them quickly, get it back. We can't just take a second to do something because we have 29 other frames, man. Got to catch up. We got to be as accurate as possible. If we give a lot of false positives, false negatives to our customers, are they going to keep using the system? I can assure you they're not. They'll give it right back. It doesn't matter if it's 70 grand. They'll give it right back. And they'll probably kick it. You don't want that. And we need to scale this to thousands of cameras if possible because, yeah, it's great to be able to put a $70,000 box somewhere to do 4 cameras, but who's going to buy that either, right? Even if it's accurate. So I'm going to note something before we go into the problems with all these different type of things. The first thing you need to understand is if your data set sucks, it's all going to be bad. Everything about it's going to be terrible, okay? So if you mislabeled this data set, if you make a car a person, if you make a cat a person, if you make a table a person, if you make your wife a bomb because you think it's funny and you think she's going to see the data set, she's not going to see the data set, she's going to see the results that she always turns up the bomb, and no one's going to think that's funny, certainly not the customer. Anyway, but yeah, just keep this in mind. Anything I'm talking about, you can make any model bad. Every model is capable of being terrible. It's up to you to stop that, all right? Okay, so AlexNet. It was big at the time, fit over 2 or more GPUs. It had to be shared and distributed to do any of these operations, but it was the first time they got this 90% plus accuracy. Latency even today is around 80 plus milliseconds, even if you're trying to convert it into something like TensorRT or something like that. Still pretty slow. I would say medium-high accuracy, and as far as you can get, it never got above what it did in the competition. They didn't really do anything else. They got this big accolades. They kind of moved on. They got their Turing Awards for Hinton and all these other things. So Hinton, the guy who's the godfather of AI, I mean, the guy was not around in 1957. I don't know why he is, but he got it. He got it, and so did LeCun and some other people based on machine learning stuff that they'd done from the 80s and onwards. The training time is very long, and I would say today's standards, the VRAM usage is not that bad, 3 to 6 gigabytes. But I don't think anybody here plans on downloading AlexNet. We're not going to spend a lot of time on it. I mean, it's cool that it's out there, and thanks for being there, but there's a lot of other stuff that's better, let's just be honest. Let's just bucketize this in transformers. And I'm just putting a note here to say that almost no one's using LSTM anymore. It was a sequential-based training. It's not very parallelizable, but it does have certain properties where you can, for you nerds out there, you can basically make it into a partially ordered Markov decision process, and you can do certain formal methods techniques to say, does this detect this correctly? Does this work? You know, and then you can do basically, if I base it on this, does this process that requires on it work? So you can do some interesting things from a provable correctness standpoint that you definitely cannot do in transformers. So the only reason to mention that is because if you are interested in this, if your boss is telling you, look, our models are terrible, everything's wrong, whatever, how do I do this? LSTM might be one thing, but it takes longer to train. So it's, whatever. Anyway, okay scaling, it depends on the size of your model for transformers. But really, this is the driver also for the H100, the A100, these big, huge server core clusters that cost a lot of money from NVIDIA. And that's because they take up so much RAM, 120 gigabytes of VRAM. Like, where are you fitting that? You can't do a 5090, you can't do a 4090, you can't do anything but the A100s and the H100s, or you could use something with unified architecture like Apple's Mac Mini or something like that, where it access all the system RAM. But that's slow, man. System memory is slow. And so is the H100. Actually, our experiments with this show that the H100, the A100s are about 1/4 the speed of a 5090 or 4090. This has a lot to do with how the caching is done on the 5090, 4090. But when you're looking at transformers, they're really kind of red across the board in what they have. And I would say accuracy is also especially that. And we can talk a little bit about why that is. I mean, basically, transformers are those things that are looking everywhere, right? They're looking all across the image, and they're saying, okay, I've trained over 1 million images, and I've looked all over this image, and that's a person. How many people are separated into 30 parts? Nobody, unless you're dead, and then why are you detecting me, okay? Leave me alone, I'm dead. Transformers are good at making relationships that aren't obvious. So the whole point of them was you can throw them at audio, you can throw them at text, you can throw them at video, and all you can put these together. You can take the encodings, these text encodings and visual encodings, and you can make something out of it. Great, you got spaghetti. But if all you wanted was meatballs, why did you make spaghetti? Okay, so like if you're not looking at the locality around it and focusing your object detection on this, you're kind of wasting a lot of time. You're likely causing some problems. And this can happen in your data sets because let's talk about some things that might be okay for transformers as far as my opinion of this. You can take it as far as the doors if you want. But like a person throwing a baseball. So if you wanted to detect a person throwing a baseball, you might want to know that there's a ball visible and a person. And you make that correlation, and that makes sense. So for human activity detection, if you have two separate things like who threw the ball that hit Carol, okay, it's the guy that was making the throw in motion and threw the ball at her. Yeah, okay, transformers can help you make that a little bit better than YOLO or something else could. But what are you doing in security cameras that requires that kind of disparate learning that goes all across the board to find something? You're probably doing nothing that actually is helpful. Okay, what you're probably looking for is it a person? Is he punching someone? Is he kicking someone? Is he shooting someone? And in that case, you're looking at their body and everything around them, what they're holding, right? So it's better, I would say, in our experiences, it's better to focus on those learning techniques and those types of machine learning to actually look at the locality around the person and then detect that thing, all right? And that's not transformers. So RCNN, read across the board in most cases. That's why you never hear about this. High accuracy, you can actually make something very accurate with RCNN, but unfortunately, YOLO came around. And YOLO has models that essentially are green across the board in various ways. It really depends on what you're trying to do. And we're going to talk about TPUs in a minute. What is their time, by the way? 8:30? Okay, got 20 minutes. All right, so I would say this is medium-high accuracy because a lot of people use the smaller models. Often they're called like YOLO V3 tiny, YOLO V8 tiny, YOLO V whatever tiny. They're trying to get small and compact and put it on a smaller GPU and put it on camera on an edge device and make it as small and fast as possible. The problem with doing that is you lose accuracy, all right? So if you make a tiny model, you lose accuracy. So I would call it medium-high accuracy. There are models that would be better than transformers, certainly, and even if you trained a transformer for 5 years on all the hardware you want, this really has a tendency, it has a capacity to be super high, but most people, the way they're training it is probably gonna be more medium-high, so I'm just putting in that category. Again, this is arbitrary grading. This is not an academic standard, so BYU, don't get on to me, man. Let me go. Let me just say this stuff. But I would say basically YOLO is the tried and true. How many people are using YOLO, just in curiosity? Anybody? Is everyone here using transformers? Does anyone even know if they're... All right. So, let's just go over this over here. And again, I just want to reiterate, it says all these things can be green, but again, your data set is going to dictate your accuracy every time and twice on Sundays. If you do not have a well-labeled data set, you're going to have a bad detector. It's just gonna happen. Get ready for it. Why is that true? Machine learning has always had an Achilles heel. This is the Achilles heel. Let me explain it. So, anytime you train a machine learning system, you're usually looking at a single metric. Mean average precision is the more common one. It means my recall, my ability to sell false positives, false negatives, my ability to say this is the image, this is the guy, these are the 3 people in this image, this is that thing, means that your percentage is this number for those things. Now, how many of your models have one thing in it? A person or whatever. So you got like a person. You're doing a gate. Someone asks you to detect a fire extinguisher. Somebody asks you to detect something else. So your class list starts building up, right? But even for a single class, the surface looks like this. These are your local minima maxima. Okay? So this is a complicated system that's being trained. You have all these weights, parameters that are across your model, and you're trying to like flip these little numbers all over this so that when you get this image that comes through the convolutional layer, did I go forward? Yeah. All right, so when you go forward through all this stuff, you're trying to go through all these weights, and at the end, it combines them into what is the thing? A person, a fire extinguisher, something else, right? That's what the actual problem looks like. In computer science, we call this simulated annealing. It's this idea that, let's just put it in a 2D graph, right? So you have this thing that looks like this, right? Well, you're training, you're kind of trying to get this metric to go up, and you kind of go back and forth between these small things and these big things, right? So let's say you're trying to get to the top. You're trying to get those maximas, get the highest mean average precision, right? So you get up here like this. There is no way for the trainer to know that it's at a global maxima or a local one. All it can tell you is if I change it in small ways, I just keep going around this hump. I can't get further. There are things called loss functions. There's things called momentum. There are various parts of the training process that essentially try to make it so that you either do random walks, so you try to go farther along that curve to get to a local minimum maxima, a different one, try something else, see if it works better, right? Or you try to go locally more. So momentum might back you off. It might say, stop going all the way over here, like focus on this guy right here. So these different metrics combine to try to change how the training is happening, how accurate you're going to be. But the problem is still this. And let me give you a different example so I can tell you why this is true. So let's say that you're trying to do the fire extinguisher and that you got 11 different classes, right? So let's say that we want to plan out your office space. You have cubicles, you have 2 offices, and you want to try to get the assignment for seating. And you have a mean average precision that's basically everyone's quality of what they believe their seat assignment is, all right? So you want to optimize everyone's seat assignment in the room for the rest of their work career and have them be happy. How hard is that? There's 2 that overlook the parking lot. There's 1 that overlooks the park. Everyone else is in the middle of the cubicle farm. And John hates the cubicle farm. Oh my God, that guy will not shut up about it. You cannot go to the water cooler. You can't go to the bathroom. The guy just won't shut up. That's what you're also trying to do in machine learning, is come up with a single metric for all the classes that you're learning, and everyone's happy about it. It's hard to do, okay? And what the basic problem here that you have is there are lots of local minimum maxima. Training can get stuck. All deep learning training is based on optimization of a single metric map score, even in multi-class, okay? And proper data labeling can significantly reduce these local minimum maxima. So this is one of your problems. It's not going to do everything, but if you label your data set correctly, you're going to have less of this. You're going to have more of this, okay? So you have a better chance to get your actual global maxima if you could. It's very rare you get a global maxima. You're not getting 100% accuracy. And you're like, 98.5, I'm feeling pretty good. 93, as long as my boss doesn't find out. 82, find another job. But you still have this simulated annealing graph on for the rest of your life, essentially, as a machine learning. This is what you're dealing with. And this is how we teach computer science, is understanding the simulated annealing graph. And I think one of the problems that we're seeing right now, certainly in our industry, is no one's really considering it like this, right? I mean, how many of you thought about this as a simulated annealing problem? Anybody want to raise their hand?
Just on the elevator.
Oh, yeah, I knew you were looking into this. Because you knew all about transformers, right? So basically, the future problems that we're looking at I'm going to divide them into 3 kind of categories here. So I think most of us are looking into transformers, self-supervised learning. So we don't want anybody to label this because, man, it would be so easy if something just solved it for us. Oh my God. If I just had a script I could run that self-labeled everything, I had 10,000 images a day coming from customers. How am I supposed to get through all this? Someone's got to come up with this. Some smart guy is going to come up with an auto-labeler that makes my life easy, and I'm going to look like a genius. Good luck. So I'm just going to say educated guess on this. Again, the doors are the end of this idea if you want. Feel free to think you know more than I do about this. I'm totally cool with that. I have strong opinions. But I think the future problems around our entire industry are really down to the data sets. I think most of us, we build our own data sets, we build our own models. We don't actually use any open source anything as far as it goes from data. We still primarily use an MS COCO as a data set. This thing is 60 to 75% mislabeled. Take a look at the data set. Just go through it. Look at what they've labeled people, and look at what they've labeled crowds, and look at how many people aren't labeled in the same image as someone else. How many times they have dogs, and there's 1 dog labeled, and there's 5 in the picture. How many times are there cars labeled where 20 of them aren't labeled? How many times is there a stadium where there's 100 people aren't labeled? Okay, so MS COCO was developed by Microsoft researchers. They wanted to help push the state of the art. It was 2000 and something, 16, let's say. And they did the best they could, all right? But it is poorly labeled, okay? It is very poorly labeled. Please stop using it. Your person detectors suck. Have you not noticed? That data set's bad. Stay away from it. Or go into the MS COCO data set and make your own. There are, I think, 3 different efforts where people have gone into Scale AI. They paid, tens of thousands of dollars probably to get other people to label this for them. And they've fixed some of them. But some of my favorite to look at, some of these that are fixed are going into, so first of all, a lot of these images are close-up shots, so they're not security camera footage. They're Facebook images or Instagram or something like this. Look inside the cars of some of these and look what they labeled. There's some that have gear shifts labeled as cars. That makes sense, I guess. Makes sense. Crazy. We also have aging data sets where people add more images to data sets, but they don't go back and fix the data sets for what they actually didn't label. So let's say that you're doing a person and vehicle data set. And you got MS COCO, so you got people, so you're like, yes, people, done. All I have to do is add these 10,000 images that we got from our parking garage that show vehicles. Oh man, this is sweet. All I have to do is 10,000 images. Well, you probably got 300,000 more images to go back through and look for our vehicles. Otherwise, you're going to be training a model that thinks that, okay, this isn't a vehicle, but this one is. That one's not a vehicle either. Okay, great, perfect. This one is, I don't know. I'm just going to put some random weights here and see what works. I want to try to get the ones that are and just like overfit for it. That's what you're doing to your entire thing. Aging data sets are the main problem we have right now in the industry. You also have a trend towards cloud. You have a trend towards FP16 int 8. And the analogy I try to give students on this is, it's like, so who was around back when we had animated GIFs on like Netscape? You know, like, do you remember this, right? Where you'd be like, oh yeah, I've got a movie, let me just post that line as an animated GIF. And it was like pixelated, like Mario Brothers looking thing for anything you do. That's what you're doing in machine learning. So you're taking a 32-bit representation, you're putting it down to 8 bits. You're saying some calibration set's going to give you some kind of understanding of what this is by going through that 32 bits of information, taking the highest frequency things and putting it into 8 bits? Are you crazy? What kind of accuracy are you trying to go for here? So our push towards TPU adoption is going to cause major problems in accuracy. And you know, you can do as much as you want from a calibration set, but if you have more than 3 classes, and if you have people, okay, so TPUs, 8-bit int, I would say you could do like soccer balls, baseballs, footballs, like simple object detection, uniform colors, all these kind of things. That's not bad. I think you could do that. That's no problem. But if you're trying to do a mission-critical system that is going to cause a response of police to come armed with AR-15s and you know their special military-grade equipment and point at a guy that's holding a bag of Doritos, did you succeed? I would say no. Because one of the things that happens is when you start building these systems, everyone just starts either trusting them or not trusting them at all. And if they trust them like we see, where people are responding, there's literally a, you know, I don't know if you guys have seen the article, but there's a guy, you know, a kid that had a bag of Doritos and SWAT, and everybody else just could hopefully, thankfully, didn't fire at him. But this is what we're dealing with. This is what we're causing as security professionals. So, you know, this is a problem for me. For me, I consider this a huge problem. Like, it's okay to go to FP16 when you're basically having the values of this and the weights and biases don't seem to make too much difference. You're still getting 99% accuracy. You still see the results. But if you're going down to int 8, I question what you're really trying to do here. And there's no reason we can't do FP16 on a TPU and put it in that. 8 is just to make it as cheap as possible and, you know, fast, if you want to say that or whatever. All this is fast as far as I'm concerned. We're in a very fast, you know, hardware market right now. Bad labeling. A lot of the data sets that I think a lot of people are using are based on internet-focused FB, Instagram, all these open data sets you can get off, you know, Hugging Face and other things. And so you're not even training on the right context. And the focal length, where the camera's focusing, the depth of field, those kind of things, they change everything about things within your model, like anchor points. So first of all, if anyone says they're anchor-free, just there's anchor points. It has to be. You know, it's going to have to put these boxes at some places. It's going to build these things based off of the relative distance from these things. And whether it shows you the anchor points or not, it still has to have some way of doing this. So if you have the wrong focus, wrong depth, whatever, you actually have different anchor points generally for what you trained on versus what you're seeing in the real world. And this can cause your boxes to be wrong. That's the first thing you're going to notice is a person. You have a close-up camera and you have a far-away camera. And the close-up camera, they're both using the same models. So when I get close, I got a box that's just this. You know, just right here in my chest. It's like me to flex or something. I don't know. But that's not really what you're looking for. So you probably need to split this into 2 models. Split your data sets into the focal lengths that you're looking at. Is it like low and just you're never going to see above like chest height? Or does it always see the person? Is it always distant? You know? If you train models like that, you're probably going to get better results than if you do try to make a universal detector for everything and just say, we got your model, enjoy your camera, all right? So things to keep in mind. Grounding dyno, that's the self-labeling stuff that most people use nowadays. The problem is, if grounding dyno is based on a person detector, that's based on MS COCO, that's based on a terrible model of detecting people, what are you labeling? A gear shift? Your wife is the bomb? I mean, if you had a good model, you wouldn't be needing it. So like, you're probably using a bad model to auto-label things and getting a bad data set. Don't do that. I know it seems like a perfect miracle, and you might have worked on 2 images you tried it on, but look at the whole data set. Don't just label the whole thing, hundreds of thousands of images, assume it's right, train it, see what the map score is, and say, I succeeded because it said 95%. That's a whole other problem. But LVLMs, transformers, large vision language models, they're more susceptible to bad labeling because they're looking at more stuff. So some of these things are looking locally. If there's something labeled somewhere out, they're not going to take it into account when they're looking at the label for a person. But if you have transformers and you have all these things mislabeled all across the image, you're actually doing more bad stuff with your bad labeling. So it's actually more susceptible to bad labeling. Attention is all you need is kind of a bad thing if your attention is on bad things. AI hallucinations are going to accelerate because the bad labeling, we're looking at scale AI and other kinds of technologies. I say technology. Scale AI is just basically hiring a bunch of novices to label for you. I don't know, do you really want your nephew labeling all your images? He's just trying to make 50 bucks. Try to get professionals. People are trained in this. And have a consistent vision. Okay, I want a person to be exactly to their elbows and their top of their head. Or I want a person to be 5 pixels around each person. Come up with a consistent vision because that's going to all dictate whether it's labeling the box it's supposed to label or if it's going to detect something else. YOLO. The problem with YOLO is the community is fragmented. We essentially had a leader named Joseph Redman. Joseph Redman was the guy who basically said, DoD is starting to use my detectors. I don't want to work on this anymore. I got ethical problems with this. Okay, I don't want a missile targeting system that's using my object detection. So he left the community. So companies are coming in and they realized a certain kind of thing about this. If everyone's looking at the map score and you can go post papers that say, we get to map scores faster, and you're a company that's trying to be the best YOLO provider, well, do you remember Volkswagen when they had the emissions stuff? How did they pass the test? They cheated. Congratulations. So I'm not saying it's happening, but I am saying that if you look at the issues, people are saying, this says 99% map score, but it hasn't detected a single cell. What is going on? And the creator's like, oh, you just did your color coding wrong. Just change your color coding. It's probably just a BGR, RGB thing. Just change it. And they're like, no, I changed that. It didn't work. We tried this for a while. We tried it for 1.5 years. It ain't real. So the trend towards TPU support, we're still going to be dealing with this inaccuracy, I think, especially if you're doing innate quantization, whether it's UIint, which is unsigned integer, which means the numbers are all positive. They're 0 to infinity, or not infinity. It's only 8 bits, so it's 256. But there's no difference really between a signed and unsigned version of this. They're both inaccurate. They don't add anything to this. They just allow you to do negative 127 to 128. And then 0 to 256. It's not that complicated. But the thing to keep in mind is false negatives and false positives reduce customer trust. And even 5% false positives when you're doing 30 FPS and let's say 100 cameras or whatever, you're still talking about tens of thousands of false notifications a day. So who's going to look at the machine or the screen or their notifications on an app if they got 10,000 false detections of someone saying this guy has a gun, but he doesn't, And it's actually not even a guy, it's a girl, and it's not actually a girl, it's a kid, it's a daughter, it's a 2-year-old baby, who's walking around pointing. This is a problem. We're losing trust in the customers, and you can't really redo the first impression you get, right? So if you do the demo is probably okay, and then you install it because you did the demo in a very focused way and you got away with it, right? And then they put it on the real thing, and then at night the cleaning crew comes in with a bucket, and all of a sudden, you got the SWAT team out. And the guy with the Doritos. So, do not trust open source labeling. I'm just going to go ahead and tell you. Academics do the best they can. They're trying to get papers published. They're trying to look good for their guys. It's publish or perish. So they're publishing papers. And they're also providing a free open source thing. Academia loves it when you give stuff away because then they can use it, right? So keep in mind, no one's trying to mess you up. No one's intentionally doing this. They're doing the best they can, but they're basically got grad students. In computer science, when we're training grad students, we have all kinds of jokes and joke problems we give to them where we torture the grad students. One of my algorithm teacher's favorite ones was okay, so me and a grad student go to the top of the roof and I drop the grad student from the roof and he bounces 5 times. What's the parabola that he did on the 3rd hop? It's like a joke, we're being tortured. So the grad students get no credit and they get to be the second author in the paper sometimes, maybe the first, if the advisor's being nice. My advisors were more the last person on the paper, but some people insist they're the first for their own notoriety or their own whatever. But I would say that it's in your best interest to label your own data. Why would you trust someone else to do this? Train a person in exactly what you want to do so you know what quality you have, and then go back and look at it. Don't just give it to the guy and say all right, label 1,000 images, and you keep training and training and training, going, I don't know why it hasn't improved. I have no idea. You need to have meetings to kind of look at this and go, all right, does everyone agree that this is a person? Does everyone agree that there's 5 people in this image? Why are we not labeling that guy? Is it too far away? Do we only want to have detections that show close up? Is that what we're trying to do here? Or why is the guy to the left just not labeled? He's the same focal length, he's the same distance. Like, why are we not labeling that guy? Have a consistent labeling policy, a scheme. Because if you don't do that, you're basically training a 5-year-old to say, look at that, tell daddy what that is. And then they say, well, that's a president, or that's a human, that's a person, that's a gun, that's whatever, right? If you give them mixed messages, they don't know how to give you the answer. They want to make you happy, right? You need to help them understand how to make you happy in this. Yeah, and again, imagine yourself teaching a 4 to 5-year-old how to classify images. What would they be confused by? So if you have a person data set and you want to add a person wearing a hat as the thing you want to do, for instance. So you made the decision to change your data set. It's currently person. You're wanting to make a person with hats also here. Well, if you tell that to then you add one image of a person with a hat in there, then you have all these images of a person and a hat in the data set that now the kid doesn't understand how to give you a good answer, right? You really need to go back and relabel all the images of a person and a hat to do this, to have any kind of data set that's going to work and give you a consistent model of a person with a hat and a person and the difference between those, all right? Now, there are certain frameworks that claim that they do multi-class well. Most of them don't. Our experience is that they mostly don't. So if you try to do boxes for the person and the person with the hat, generally your model's going to be worse than if you actually just make a decision, what do you prefer? In this situation, do you label a person with a hat or do you label a person? Now, you can do other things, like we have databases, other things in our company where essentially it's labeled both the things, but when you're exporting to a certain type of model, you export only the thing that's the most important, the most significant, the thing that you actually want for that model target, right? That's a way to do it too. Have a database, have all your marks in there and then export the thing you want. Like if it's just a person detector, just export it as a person. If it's a person with a hat and person, export it with the distinction, right? Does all that make sense? Everybody following? How to correct your object and activity detection, focus on good models. Don't just trust experiment results from papers. If they say, oh, we beat these guys because we have a better map score, are you sure they didn't use a terrible data set? Is it saying MS COCO? Because they all say that, because all of academia understands if you use a baseline like MS COCO, then you can just say, I compared myself to these guys, I can use their experiment results and I can show you these results and then I get the paper published, okay? The problem with that is, like I told you, it's between 60 and 75% mislabeled in MS COCO. So what did it learn? If it has 60% map, if it has 70% map, if it has 99% map score, what does that mean? Okay? So when you're looking at map, you want to test for failure. You want to say, what am I actually trying to test in the real world? Test it against the real images, and don't even worry about the data set, because if it doesn't give you the right results for the real world with the lighting you're expecting and everything else, it's not 98% map. Don't even worry about that number. The best thing you can use that for is just understanding, is your training done? All right? And that's about where you can use it. Spend time creating data set conversion tools to fine-tune models between YOLO, LVLM, transformers, whatever you want to do. So a lot of them take YAML, a lot of them take JSON files. You kind of have to build things to translate between them if you want to test these out. So take a little bit of time or look for the tools online. Some of them exist. And I would also recommend, there are some summer courses you can take. There's also just YouTube video. A lot of these faculty will put their YouTube sessions on there, like Stanford, MIT, CMU. It's going to be deep. You don't have to know all the math necessarily, but understanding the concepts may help you understand more. And it's probably very useful just to understand, what does academia think the right thing is? I know we have a very polarized news cycle that basically says science sucks and professors are idiots, but man, that ain't true. It ain't true. So please, try to look into this. See what the experts are saying, because they've spent 40 years looking into this. And they understand, they've read all the papers. They've looked at Rosenblatt's machine from 1957. They understand what's going on. A lot of them can do the math. They can show you proofs if you listen to them. So why not? Take the course, look at it, spend a few hours, a couple of weeks, and get through it. Data labeling's core, LVMs may solve everything, but it's unlikely. Everyone's going to keep saying this. Just use ChatGPT, just use Claude, just use whatever. I'm telling you, you can trust that if you want. We've had AI winters before in the 80s and 90s. We'll have another one coming up, I would think. YOLO models are trending in the wrong direction just because they're being led mostly by companies. If you look at the open source community around this, like for instance at Darknet, other places, it's probably a better place to start looking than it is looking at a commercial offering, to be honest with you. Focus on what your customer needs, not just what is easy. No customer wants a solution that gives wrong answers, and a system that even has 1% false positives could result in tens of thousands of false positives a day. All right, thank you. Any questions before we wrap up? You guys go to the keynote? Well, thanks for your time, everyone. Have a good rest of the session.